We will introduce the hidden Markov model, which is a very important probabilistic model that can be applied in many applications. In early years, around 1980s, speech recognition has been already studied for years. However, uh, the performance of recognition at that time was unacceptable, and the related study becomes acceptable when the hidden Markov model was proposed to be employed in speech recognition. And even for today, right now, many speech recognition technology has adopted the deep learning technology. However, the most state of the art, the most efficient and feasible way to implement a speech recognition system is is still using hidden Markov model associated with deep learning technology. So it's quite important to understand the idea of hidden Markov model. And also, not only for speech recognition, for many multimedia content analysis systems, hidden Markov model was widely employed in many applications. We describe Markov model first. As we know in probability, the joint probability of three random variable probability A, B, and C can be expanded by a chain rule. That is probability C multiplied by probability B given C, and then multiplied by probability A given B and C. And such chain rule can calculate the joint probability of many random variables. However, if the numbers of random variables is quite large, this calculation would be very inefficient. So the idea of Markov is that they assume that each of the condition distribution is independent of all previous observation except the most recent. That is the so-called first order Markov chain. That means here is an illustration. The value of x2 is only depending on the value of x1. The value of x3 is only depending on the value of x2, and so on. And this is the so-called first order Markov chain. And for the second order Markov chain, the probability of S3 may be depending on S2 and S1. The probability of S4 may be only depending on S3 and X2, and so on. And by this assumption, we can largely eliminate the relationship between different variables, so that to calculate the joint probability of S1 to Xn, theoretically we can expand it by the chain rule. However, we can also assume the first order Markov property. That means the probability of Xn given by S1 to Xn minus 1 can be equal to probability of Xn given only by Xn minus 1. So this is the first order Markov property. And with this property, we can simplify the calculation of this joint probability by simply this one. So we can see here, for any probability of Xn, then we can calculate the probability of Xn given by Xn minus 1. We can largely simplify the calculation of joint probability. So here is an example showing a weather condition. So what's the probability that the weather for 8 consecutive days is sun, 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 rain, rain, sun, cloudy, sun? Okay, so we can build a model, a Markov model, to show the probability of one weather type change to another weather type. For example, uh, if the first day is rain, then the second day, then the weather changed from rain to cloudy, is the probability is 0.3, and the probability of from cloudy day change to raining day is 0.2, and so on. So given this model, this is an explicit Markov model, and the observation O, like the 8 consecutive day is sun, 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 rain, rain, sun, cloudy, sun. So given this model, the probability of such observation is that we know that it's the state 3, state 3, 3, 3, because the state 3 means sunny. So this is the state 3, 3, 3, 1, 1, 3, 2, 1. Okay, so given this model, what is the probability of such state sequence occur? And the probability is easily to be calculated. That is, originally it's sun. Okay, so the probability of the state 3, and then the second day is also sun. So the probability of the first day is sunny, and the second day is also sunny, and then again also sun. So the probability of sunny change to sunny. Okay, so here is the sunny change to sunny. The probability is 0.8, and so on. And then the sunny change to rainy. So the probability of sun change to rain would be 0.1, and so on. And then rain to rain, rain to sun, sun to cloudy, and cloudy to sun. So we can calculate the probability. The original probability of the state 3 is pi 3, and then the transition probability change from sunny to sunny is A33 here. And here we also calculate the probability of sunny change to rain, so A31, and so on. And this matrix showing the all transition probability between different states. So now pi 3 is assumed to be 1, A33 is 0.8, and then A31 is 0.1, and so on. So that finally the probability of a consecutive days with such weather condition is this. Okay, and this is a very classical example showing explicit Markov model, and how can we calculate probability based on such explicit Markov model. And know that in the following material, we mainly extract data, extract information from these two very important literature. The first one is a book called Fundamental of Speech Recognition, published in 1993. And you can see that the author is Rambuner and Zhuang. And actually, Zhuang is originally from Taiwan, Zhuang Binghuang. He is a Zhongyan Yan Yuan Shi. Okay. And another very important paper published in 1989 is published in Proceedings of IEEE. And the paper title is a tutorial on hidden Markov model and a selected application in speech recognition. And you may remember these two important researchers about hidden Markov model. Now let's go to the hidden version of the Markov model. Assume that you are in a room with a curtain through which you cannot see what is happening. On the other side of the curtain, there is another person who is performing a coin toss experiment, who may use one or more coins. The person will not let you know which coin he selects at any time. He will only tell you the result of each coin clip. And so the only observation you can know is the the result of head or tail. So assume that the another person perform T flips, and then he may tell you that okay, the first time the result is a head, the second time the result is also a head, the third time is a tail, and so on. So the question is, how do we build build a model to explain the observed sequence of head and tail? The problem is we don't know how many coins and which coin the person has to select. And for each coin, the result may be head or tail. So assume that there is only one coin. So we can build a one coin model. So given if another person has only one coin, the state of Markov model may be represented like this. One state represent head, another state represent tail, and the probability of a head change to head is pH. The probability of head change to tail is 1 minus pH. Okay, and so on. So if the observation is head, head, tail, 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 head, tail, tail, head, then we know that the corresponding state is 1, 1, 2, 2, 2, 2, 1, 2, 2, 1. That is because the meaning of each state is expressive. Okay, if the result is head, then it must be state 1. If the result is tail, then the state must be 2. And this is called a one coin point. And once we know the observation, the observation of result, we already know the corresponding state sequence. Okay, and this is actually an observable Markov model because, as we said before, once we know the observation sequence, we already know the state sequence. Okay, and this is the case when there is only one coin. If there are two coins, then we can build a model like this. The first step means that the first coin is selected. The second state means that the second coin is selected. Okay, and the probability of select the first coin and the next we also select the first coin is A11. The probability of select coin number 1 and then select coin number 2 is 1 minus A11. And when we select the first coin, the probability of head is P1. The probability of tail is 1 minus P1, and so on. So given the observation sequence, head, head, tail, 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 head, tail, tail, head. Further, for the first head, we actually don't know which coin has been selected to give the head result. So the result may be, the state may be 2 or maybe 1 actually. So the observation sequence, the corresponding state sequence may be 2, 1, 1, 2, 2, 2, 1, 2, 2, 1, or maybe 1, 1, 1, 1, 1, 1, 1, because we may also give such observation sequence if we only select the first coin, or it may be 2, 2, 2, 2, 2, 2, 2, and so on, or maybe 1, 2, 2, 1, 1, 1, 2, 2, 2. Okay, so for all this state sequence, we may generate such observation sequence. And the problem is we don't know what exactly is the state. That means we don't know what exactly which coin is selected to generate such head or tail. And this is the so-called hidden Markov model. Okay, so for now we know why we call it hidden, because the only information we know is the observation sequence, is the result of head and the tail. We don't know which coin We don't know how the person select the coin to generate such information, such result. So we call it hidden Markov model. And also, there may be 3 coins. So we use one state to represent one coin, and then the observation sequence is also head, head, tail, 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 head, tail, tail, head. And the state sequence to generate such observation may be 3, 1, 2, 3, 3, 1, 1, 2, 3, 1, or maybe 1, 1, 2, 2, 3, 3, 1, 1, 2, or 3, 3, 1, 1, 2, 2, 1, 3, 1, and so on. There are many possible state sequence that can generate such observation sequence. And this is also an hidden Markov model. Now you have the idea of hidden Markov model, why we call it hidden. So how can we systematically describe a hidden Markov model? There are a few basic elements. The first element is the numbers of state in the model. So to define a hidden Markov model, we have to define the numbers of state. And then for each state, the numbers of distinct observation symbol is m. Like the example we said before, for each state, the observation is head or tail in that case. And then we have to define the state transition probability A. The state transition probability Aij is that the probability of the Qt is that at time instant t, the state the state numbers is Qt. So if Qt is equal to I and Qt plus 1 is equal to J, that means we jump from state I to state J. And Aij means the probability of we jump from state I to state J. And this is the so-called state transition probability from I to J. And the observation symbol probability distribution is that given that we already at the state J at time instant t, the observation OT is equal to Vk. The probability of such observation at state J is the so-called BJK. Okay, so J here means the state, K here means the observation symbol, and also the initial state distribution. That is when we start this model at the time instance number 1, it start at state I. The probability of we initially start from state I. So this is called pi I. So to describe an HMM, we usually use the compact notation. Lambda is equal to AB pi. That means the transition probability, observation probability, and the initial probability. And based on hidden Markov model, we mainly have to tackle 3 basic problems. The first problem is probability evaluation. The problem is defined like this. Given the observation sequence O, that may be composed of O1 to OT, that is a sequence, observation sequence, according to the result, consisting of the result at different time instance. Then a model lambda AB pi. How do we efficiently compute probability of all given lambda? So given this model, how likely this state sequence appear? So the probability of the observation sequence given by the model. Okay, that is also see that how do we compute the probability that the observation sequence was produced by the model? And this probability is usually used to score how well a given model match a given observation sequence. So this is the first problem we will emphasize first. The second problem is optimal state sequence. So also, given the observation sequence O and the model lambda. How do we choose the corresponding state sequence Q from Q1, Q2 to Qt that is optimal in some sense, that is best explain the observation? Okay, so as we said before, in the two-coin model, uh, the result of head, head, tail, 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 that may be generated by the state sequence 1, 1, 2, 2, 1, or 1, 1, 1, 1, 1, or 2, 2, 1, 2, 1, and so on. So which is the optimal state sequence that most likely explain, that most likely generate observation and observation sequence statistics? So we want to uncover the hidden part of the model, that is to find the correct state sequence. And for practical situation, we usually use an optimality criterion to solve this problem as best as possible. So this is the second important problem. The third important problem is the most difficult one, the parameter estimation. So how do we adjust the model parameter lambda is equal to AB pi to maximize probability O given lambda? So we want to optimize the model parameter to best describe how a given observation sequence comes about. And the observation sequence used to adjust the model's parameter is called a training sequence because it is used to train the hidden Markov model. So for the training process, we will collect a lot of training sequence and use this training sequence or the training observation sequence to adjust the model parameters A, B, and pi. And this is the third important problem. And this is the most difficult one. We now solve the first problem. So the first problem is that given the observation sequence O from O1 to OT and the model lambda is equal to AB pi, how do we efficiently compute probability of O given lambda? That is the probability of the observation sequence given the model. So at each time instance, we may have n possibility state. So because we have n states, and for each time instance, um, each uh, each of the n state may be possible to generate the observation. So at each time instance, we have n possibility, and because we have t time instance, so the probability of all sequence may be n multiplied by n multiplied by n, and so on. And therefore, we have n to the power of t possible state sequence. And this would be a very large number. So if we consider only one fixed state sequence Q, that means at time instance 1, the state is Q1. At time instance 2, the state is Q2, and so on. Then given this state sequence, the probability of the observation sequence given the sequence is this. Probability O given Q and lambda. And this probability can be calculated by multiplying O observation, so P small ot given Qt and lambda. And we multiply from t equal to 1 to capital T. This probability, we have assumed statistical independence of observation. Therefore, we get probability O given Q and lambda is equal to the multiplication of T observation probability. So this is the first at the first time instance, and at the Q1 state, the observation probability of O1. So this is the time instance 1. And this is the time instance 2. At time instance 2, the observation probability, and so on. And we multiply O capital T observation probability to get the probability of O given Q and lambda. And note that this is only for calculating the the probability given by this state sequence, and we have n to the power of t possible state sequence. So this is a very computational expensive process. And the probability of such state sequence. So the calculation mentioned above is just specific to one state sequence. And what's the probability of such state sequence to be generated by this model? That is the probability of Q given lambda. And the probability should be the initial probability initial at Q1 and then jump from Q1 to Q2. So we multiply the initial probability by the transition probability from Q1 to Q2, and then multiply by the probability of the transition probability of Q2 to Q3, and so on. Therefore, the joint probability of O and Q, okay, the O and Q occur simultaneously is simply the product of the above terms. So that given the model lambda, the probability of such state sequence generates such observation sequence is multiplied by the probability O given Q lambda and the probability of Q given lambda. Okay, so the probability of O is obtained by summating this joint probability over all possible state sequence Q. So here is just given the model, the the state sequence Q is generated, and in such state sequence, the observation sequence is generated. Okay, and then because we have various state sequences that are possible to generate the observation Q, so we have to sum over all possible state sequence, and remember that we have n to the power of t state sequence. So the probability of O given lambda is that we summation all possible state sequence and this probability value. So mathematically, we can represent probability O given lambda by this equation, and this would be very computational expensive. So the solution to the problem 1 is that we want to derive a more efficient way to calculate such probability. An efficient way to solve the first problem is the Forwalk procedure. In the Forwalk procedure, we define the probability of a partial observation sequence O1 to OT and the state I at time t given the model lambda. So this probability alpha ti is defined like this. Given the model, we care about the time instance t. The time instance t, assume that the time instance t, the state is at I, and from the time instance from 1 to t, we have observed O1 to OT. So this is the partial observation sequence. That means we already observed t small t observation, and at the time instance t, we stop at state I. Okay, so this is the so-called Forwalk procedure, the probability of partial observation, and this value can be calculated iteratively by the following process. So initially, what is alpha 1 I? The alpha 1 means at the time in instance 1, we stop at state I. And this probability is defined by pi I multiplied by BIO1. Pi I because we initially start at state I, and at the state I, we observe O1. So this is the observation probability. This is initial probability. So the alpha 1 I is calculated like this. The most important one is the induction process. Given alpha 1 I, we can calculate alpha 2 and then alpha 3. So any alpha t plus 1 j, we can calculate it by summation O alpha ti, okay, where I is equal to 1 to n. So now at time instance t, t plus 1, we stop at the state j. And what state can jump to state j? Actually, we have n possibility. We can jump from this to this. We can jump from this to this. We can jump from this to this, and so on. So here, we summation all possible state I. And if we jump from state I to j, the transition probability is aij. For example, if we jump from state 2 to state j, we will multiply the transition probability a to j here, and then we jump to state j. Then we multiply by the observation probability bj, given and we observe ot plus 1. So here is the induction process. We can calculate alpha t plus 1 based on summating all possible alpha ti. So this is the induction process. And the termination condition is that we can calculate probability O given lambda by sum all alpha capital Ti. That means at the final time instance capital T, we summation all alpha capital T, maybe alpha capital T1, alpha capital T2, and so on. We sum all of them. Then we can get the probability O given lambda. So this is the whole Forwalk procedure, and this is a more efficient way in contrast to calculating all probabilities given by m to the power of t state sequence. So here is an illustration showing the relationship between alpha ti and alpha t plus 1 j. We can see that at state j, we have n possibility start point. We can start from this one and jump to this one, start from this one and jump to this one, and so on. And for each state j is equal to 1, 2, or 2n. So for each state, here we can sum all previous states. Here we can sum all previous states, and so on. And finally, we require on the order of n squared t calculation, because for each time instance, we consider n state, and for each state, we consider the previous n state. So at time instance, we need n squared operation, and because we have capital T, time instance, we totally need n squared t calculation, which is much fewer than the original one. The original one, we have n to the power t state sequence, and each time and for each state sequence, we need 2t operation, and this value is much larger than the n squared t. So the Forwalk procedure is a much efficient way to solve the first problem. Before we go to the solution of the second problem, we also define another procedure called the backward procedure. In this procedure, we define the probability of partial observation sequence from t plus 1 to the end. So this is another way, another direction to calculate the probability. So given the state I at time t and the model, So the beta Ti is defined like this. Given the model, and at time instance t, we are at state I. So given these two conditions, we want to calculate the probability of O t plus 1, O t plus 2 to O capital T. Okay, that means this is the probability of we start from state I, and then we jump to all the others states to the end. Okay, and this procedure can also be described as a iterative procedure. So initially, we initially at the end of the whole state. So initially, beta Ti is equal to 1. Beta Ti is equal to 1. And then we can calculate beta small ti based on beta t plus 1 j. So the beta Ti is the summation of all beta t plus 1. So from state I, we can jump to state 1. From state I, we can jump to step 2, and so on. So we sum all possible succeeding state. Okay, so the beta Ti, beta t plus 1 j multiplied by the transition probability and the observation probability at the time instance t plus 1. Okay, so this is how we calculate the beta Ti. Now we are ready to solve the second problem. The second problem is, given the observation sequence O and the lambda, the model lambda, how do we choose the corresponding state sequence Q that is optimal in some sense, or we can best explain the observation? So given the observation sequence, we want to find the most appropriate state sequence that can generate such observation sequence based on alpha and beta. Now we define the quantity delta Ti. Delta Ti is the maximum of the probability. What probability? Given the model lambda, the probability of from time instance 1 to time instance t minus 1, we already know this partial state sequence. And at time instance t, we are at state I. And from state I, the following observation sequence is OT plus 1, OT plus 2, and 2 OT. Which is the best score along the single path at time t, which accounts for the first t observation and end in state I. So the delta Ti means the best probability, the highest probability along a single path. This path end at time t, and the so-called best path accounts for the first t observation and the end in state I. And by induction, we have delta t plus 1I is defined like we maximize delta Ti multiplied by the transition probability and the BJOT. Okay, that means we may have several paths to end at the state I. From them, we select the best path, like this path to this one. And then we may have several paths to go on. Okay. So this is delta Ti. And if we want to calculate the delta T plus 1I, like here, we need to find all possible, there may be many possible states, like from this may be the best path from here and then go to here, and then this is the best path from here and then go to here, and then there may be another path from here to here, and we just maximize the best path. So maybe we found that going from this path and then go from here calls the largest probability. And this is defined as delta Ti. Given delta Ti, we can use the following algorithm to solve the second problem. This algorithm is called the Viterbi Algorithm, which is very, very famous. And the essential idea of this algorithm is actually similar to the dynamic programming that we have learned in the algorithm class. The algorithm is working like this. So initially, the delta 1 I is defined by pi I multiplied by bi01. That means we start at state I, and at state I, we observe O1. And the recursive process is defined like the delta Tj is considering all possible delta T minus 1I and jump from state I to state J and observe OT at state J. We consider all the cases and then find the maximum probability that at time instance T, we stop at the state J. We find the highest probability to cause this situation. And the phi Tj is to store the parameter that generate the delta Tj. That means we calculate the highest probability and store the state sequence that cause the highest probability at time instance T. And finally, the termination step. The termination it terminate at time capital T. So the delta capital Ti, we found the highest probability, or we find the maximum of all possible delta Ti, because right now I may be from 1 to n. We find the highest probability. And then Qt star means the parameter, the state sequence generate delta Ti. So at time instance capital T, the delta Ti means from the beginning to the end, the highest probability to end at state I is called delta Ti. Okay, and I may be 1, maybe 2, maybe 3. So we calculate the highest probability to end at state 1, state 2, state 3, and so on. And finally, how can we find the best sequence that generate a given observation sequence? We do backtracking. So starting from time instance capital T, we backtrack the state, and then the Qt star is phi T plus 1, Qt plus 1, and the small t is from capital T minus 1, capital T minus 2, and so on. You may find that the algorithm is quite similar to the Forwalk procedure we mentioned above. In fact, the major difference between Viterbi and the Forwalk procedure is the maximization over previous states. In the Forwalk procedure, we sum all possible situations over previous states. So you may look back the Forwalk procedure. We do summation over all I equal to 1 to n. And in the Viterbi algorithm, we don't sum over all previous state. We just found the maximum, the highest probability. So that's quite similar, but a little bit different. And now the most difficult problem is the learning problem. So how do we adjust the model parameter lambda equal to AB pi to maximize the probability of given lambda? So how can we adjust lambda such that this model generate the observation probability with the highest probability. Okay, so chosen lambda equal to AP pi such that its likelihood, that is the probability of given lambda, is locally maximum using an iterative procedure. And this iterative procedure is called Welch algorithm. It's also known as EM algorithm or forward backward algorithm. The most well-known name may be the EM algorithm. And this algorithm, the concept of this algorithm, is not only used in hidden Markov model training. It has been widely used in many model training. So how do we do that? We first define the probability of being at state I, being in state I at time t, and the state j at time t plus 1. And this probability is denoted by psi t ij. That means no matter how the state change, it stops at state I at time instance t, and then it jumps to state j at time instance t plus 1. And no matter how it goes, okay, so this probability is defined by given the lambda and the observation probability. The qt is equal to I, qt plus 1 is equal to j. No matter how the beginning, from the beginning to the state t, to the time instance t, and how the following process goes. We don't know. We don't care about it. We just calculate the probability of the state I jump to step j at time instance t and the time instance t plus 1. And this is defined as the psi t ij. And how can we calculate the psi t ij? It's actually can be calculated like this. So given the lambda, given the model, and the probability of such observation probability and which is such state transition divided by the total likelihood. And the denominator can be calculated as alpha ti multiply the transition probability and the observation probability and then the beta ti plus 1j. So the alpha ti we have defined in the forward procedure. The beta t plus 1j we have defined in the backward procedure. Okay. So the psi t ij can be calculated like this. And then we also define gamma ti. Gamma ti is equal to given the lambda and the observation. At time instance t, we are in the state I. So no matter how the beginnings go and how the following process go, we just care about at time instance t, we are in the state I. So this is the probability of gamma ti. So the probability of being in state I at time t, given the observation sequence O and the model, is the gamma ti. And actually, gamma ti is equal to summation of j equal to 1 to n. That means we sum all possible situations starting from state I and then to j. And j may be there are n possibility. Okay, and we start from state I. So the relationship between gamma ti and psi ti ij is like this. And we can also calculate gamma ti as this. And that is probability O qt equal to I given lambda. Okay, so we can calculate it by alpha ti multiplied by beta ti divided by the total probability, likelihood probability. And we now know that summation t equal to 1 to capital T minus 1 gamma ti is the expected numbers of transition from state I in the observation probability. So this is the considering all time instance. The expect numbers of transition from state I is this value, and this value is the expect numbers of transition from state I to state J. Here we see that we sum over all time instance. So this is the expect value for all time instance. We jump from state I to state J. Okay, so by considering all these properties, we now can estimate the pi, the initial probability, transition probability, and the observation probability. For the initial probability uh, of the state I, that would be the expect frequency or the numbers of time in state I at time equal to 1. That is the gamma 1i. So the gamma 1i would be the expect numbers of times in state I at the time equal to 1. And then aij may be the expect numbers of transition from state I to state J divided by the expect numbers of transition from state I. So here is the summation over sin Tij divided by summation over gamma Tij. And the beta and the bjk is the expect numbers of times in state I and observe symbol vk divided the expect numbers of time in state J. So here we can calculate it like summation over t equal to 1 to capital T, such that the observation OT is equal to Vk and the gamma Tj divided by all possible gamma Tj. So that's the estimating probability of the initial probability, transition probability, and the observation probability. We now recall the EM algorithm that has been described to train the Gaussian mixture model. For the hidden Markov model case, we can also imagine that we first randomly initialize the initial probability, the transition probability, and then the observation probability. After this initialization, we can estimate the alpha Ti, beta Ti, psi Ti, and the gamma Ti that has been defined in the forward procedure, backward procedure, and the Viterbi algorithm, and all the others. And based on the estimate, alpha, beta, gamma, then we can estimate new initial probability, transition probability, and observation probability. And with the newly pi AB, we can again calculate the new alpha, beta, gamma, and then update the pi AB, and so on. So this is the so-called expectation maximization algorithm. And we can use the same idea to train the hidden Markov model. So given a large numbers of observation sequence, we can update the model parameters by given the observation sequence, and then find the best parameters to maximize the probability of the model generate such observation sequences. And that's all we have for the three major problems of hidden Markov model. And in fact, although we just mentioned the first order hidden Markov model or second order hidden Markov model, there are actually several variations of hidden Markov model that has been widely used in different applications. One example is the so-called algorithmic hidden Markov model. That means for every two states, we have a state transition between them. That's called algorithm. Another one that is widely used in speech recognition and many other applications that has temporal order is the left-right hidden Markov model. So here we can see that the state transition can only go from left to right, not from right to left. So this is another structure. And also some study propose parallel paths left-right. So from step 1 to step 6, we may have different paths. We can go through this, or go through this. So there may be some parallel paths. And for some case study, we just give you an example published in year 2002 that was used to extract highlight from baseball game video with hidden Markov model that was published in International Conference on Image Processing. And the idea is that they can build hidden Markov model to describe some important events in baseball videos, such as a nice hit. So to generate a nice hit, there may be start from a pitch view, and then a catch view, and then maybe the ball is hit out. So the camera switch to the running view, and then maybe the runner may catch up some base. So there may be some close up. So we can use the transition between these states to show a nice hit, and then maybe a nice catch. So starting from a pitch view, and then there may be a catch close up, or there may be a running close up, and this would be a, a nice catch or home run. So starting from pitch view, and then maybe the ball fly to the outfield, and the camera shows the audience view, and then there may be the runner close up, then this would be a home run, and so on. So if we can recognize the view of the camera, we can check whether they follow some state transition, but of these hidden Markov models, and then we can estimate the probability of some important events. And in this work, they propose some features, some visual features like field descriptor, age descriptor, grass and sand, player height. They use such features to recognize the meaning of each view. And then for each highlight model, they can compute the optimal state sequence by the Viterbi algorithm, and then check the probability derived by the state sequence. And for the model that generate the highest probability and may exceed some threshold, then we say that the given video clip has some spatial important events like a home run. So this is a very simple case study used to using hidden Markov model to do multimedia content analysis. And then there are many other applications. There are many other studies. If you are interested, please refer to some related literature. And if you are interested in using hidden Markov model to do research, here are some related resources. You can use MATLAB Toolbox to train your hidden Markov model, or you can use some C library, or use the HTK speech recognition toolkit to train your own hidden Markov model.